are here. People might be still coming in. So let's hear. Good afternoon, everyone. So for those in person here, hello, and for those who are online, we are currently attending a special edition of CRADLE Talks. This is the second part of a two-part webinar series on space robotics. The first session taking place last week with Dr. Chris Kunskill. I'm not sure if you attended that, but it was a really great session. So Dr. Chris Kunskill is a principal consultant for space at Momentum. So my name is Paul Beniket. I'm the technical project manager of CRADLE. And for those of you who are new, this is CRADLE Talks. It is a series of seminars and discussions highlighting the research and case studies from CRADLE, which means the Center for Robotic Autonomy in Demanding and Long-Lasting Environments. This is a really long acronym. So this is an ETSRC prosperity partnership between the University of Manchester and Cologne. Right, so for today, the second part of the webinar series, we are doing a live fireside chat with Team CRADLE-MoLES3. I'll just call ourselves Team CRADLE. That's so Team CRADLE recently returned from a trip to the ESA European Astronaut Center and the DLR, that is the German Aerospace Center, Luna analog facility for the second Space Resources Challenge, and which we will know more about later. Right? So, as previously mentioned, we have with us the team who worked so hard, more than 9 months, from proposal to deployment, and entry for the challenge, which we now call MoLES3. Can anybody define what MoLES3 is?
That's a good question. I'm not sure how the name came to be or renamed the system. I know the name is modular. Oh,
No.
mobile. I don't know. Mobile. It will definitely be lunar. And then the E3 is there's three E's: excavation. Oh, and the ESA separation, yeah.
Good. Well,
How well do we know the name?
yeah, so
We know the system very well.
it is in your jackets if you want. So MoLES3 stands for Mobile Lunar Excavation and Size Separation System. So there we go. So we also want to acknowledge the rest of the team who contributed to making this project a success. Let me just flash their faces in here, so you can see their. Oh, there. Yeah, there you go. So we got yours truly, and then we got people from Momentum. We have Johnny for robotics. We have Marty for as our industry lead, and of course we have I think there are and who is taking pictures of video or basically your phones. So you're running the organization.
Hello everyone, welcome to this session. My name is Tanesh Khan and I'm a technical specialist. So I was running through our team in this project, designing wheels to integration of sustainability to this project.
The and the system so that the exploration and the positions and interactions how to control
Hello everyone, my name is Sharon and I'm a first year PhD at CRADLE and I'm responsible for the electromechanical integration of both robo and mitigation systems.
My name is Christopher Fish. I was in charge of everything to do with the beneficiation side, so that's we take the moon dust and we separate it down into different sizes. So certain particle sizes can be used to make oxygen for supporting future missions on to the moon. I was also involved in transporting the regolith from the rover to the beneficiation system. We had a mechanism for how that transported across.
Could you hold the microphone a bit closer so we
Yeah.
So just what you did on the project and your role.
Yeah, Kate, Professor of Space Technology, I was the academic lead for the project. And so some of the research that we've done in my group were kind of the seed of the start of the design. And it evolved from there.
Okay. Great. Yeah, so just from the people online, they say they're having audio and technical issues, so please, if you can make this not shout, but you just have the volume up a bit. Okay, thank you guys. So now to our agenda. I think we can divide the discussion into different stages of the project. So we have, of course, the initialization and proposal stages. Then we have the development stages, and then we have the deployment stages. It's quite interesting. Well, to start with the initialization, well, the story is that I remember Professor Kate Smith. We did a meeting with Amentum about what CRADLE can do in space. And of course, there's a lot of things to do in space, and having a background in space robotics, the space space systems research group. We had a meeting with them, and I remember Professor Kiskin sending a call from ESA to join the Space Resources Challenge. And of course, given that this is a good opportunity for CRADLE, we took the call. There's a lot of things involved in here, but if my question to maybe Sharon for now, if you can discuss what are the requirements of us joining the ESA Space Resources Challenge. So what are the technical?
So we can entirely have the requirements in 4 stages: price sorting, beneficiation system, excavation, power and mass requirement, and as well as dust mitigation. So basically, for the excavation, we have to excavate a total of minimum 15 kgs of regolith. And as well as for the beneficiation side, we have to beneficiate almost 5 kgs between 100 to 500 micrometer. And for the power requirements, we shouldn't cross more than 300 watts of power for the entire system, and as well as for the entire mass, we shouldn't cross more than 60 kgs. And one of the main part would be the dust. So whichever team has the generated less dust, because the lunar layer can actually cause more dust when you excavate it, they will get more points. So that's the entire requirements of the competition.
Great. So, and now I think that between Chris and Kate, if you can answer, sorry for the hotspot. This is an idea that is already existing from a research project, right? So basically, who came up with the idea of the concept of MoLES3, and how did this idea evolve from discussions about anything existing?
So the LES cube was an initial idea from a PhD student of mine, Gunther Just, who is now in ESA, in the robotics team from ESA. And his work was on excavation and beneficiation. We saw this gap within that domain that people hadn't really studied and looked at the excavation side. And also, how do you optimize it if you've never integrated, so the excavation integrated with beneficiation, kind of reduce system mass, and that's where we were kind of going with that. Obviously, we learned a lot through this process, and maybe Chris can kind of elaborate on that.
Yeah, so this is brilliant. There's the video you can see on the screen shows the LES, so that's the lunar excavation system. I think the concept was it's a robotic arm, and the filtration happens through the arm. So there's a filter on the front, but at different stages along the arm, you can see on the screen, it will filter it into different particle sizes, and then there's a cam mechanism at different points for releasing it and storing it. So we considered initially, can we take this design and scale it up and work it, make it a much larger system? And we run some initial tests on lab sieves of diameter 100 mil. So we increased the diameter. The filtration rates we were getting, we couldn't filter fast enough. So we wanted to come up with a new idea of can we separate the system to have the filtering in a static system, which stays where it is, with quite a large diameter, and then have the robot just for excavating. And that led us to the moles idea. But we had some other concepts that we explored. So finally, what we did was essentially lab sieves stacked together. With that would vibrate, and we would bring the material to this system. But other ways of filtering, we considered a trommel idea, which is like still sieves, but they rotate around. So as you put the material into an angled spinning, what's the word?
Spiral.
Sort of like this cement mixer machine. So I think that's the kind of design, and you'd feed it in. But the reason we stay away from that is we weren't confident that we'd be able to get the accuracy of the particle sizes, because that system would just let the material keep flowing through it. Yeah, I think that's
Great, it's a great intro. And then, of course, what you're seeing in this video is the proposal submission that we sent to ESA, knowing that after, I think, March time, we were included as one of the finalists, particularly 8 finalists who will be competing in Germany to do the deployment. Then we celebrated a bit and then get to work. But of course, there were challenges along the way, and it involves around setting up the facilities and just starting. Really, there's a lot of inertia. So my question is to our technical specialists, Danish and Sky. So from a technical standpoint, how did you start preparing the facilities and equipment, and what early hurdles did you encounter setting up the lab and test areas and that mimics the regular vision? So let's start with Danish.
And the first step was to recreate the situation, the conditions and environment that the rover has to go to the lunar facility. Things like rough terrain, dark environment, and of course sand. So we established a small sand pit. We used building sand because we didn't have the actual regular stimulant. So we used building sand to make our own small mold pit, which was our testing ground for the whole development process. And it actually was very effective. We were able to optimize the wheels of the robot on this. We tested the navigation of the robot, we tested digging, and it was very helpful. The hydrodynamics lab where we set up the sand pit was not fully light controlled, but we were able to control the light to some extent by using blinds and turning the light off, and that's how we decided our perception sensors.
Great.
One thing I just tried to add is you can see the pictures of the hydraulic sand. The sand is not deep enough, and that is very important for digging evaluation because in the ESA facilities, the regulus is not like deeper than 3 meters everywhere. So it's like full of sand and regulus. If you have a shallow sand pit, your arm will hit the floor, and that performance will be like moisted and not useful. So for that, we add like 2 tons of sand. We order the building sand and we transport it from like the rock store using the forklift and the crane to deliver this sand in the hydraulic lab. And we still keep this sand there for a short period of time. So that will be useful for research experience.
Yes. So yeah, that was quite an experience seeing you just carrying this to the it's a mezzanine area, so mezzanine of the hydrogen and stuff. So lovely, thank you to our hydrodynamics team if you're watching this. Thanks for being so kind to give us. And thank you, Kate, for arranging as well for this one. With your network. So okay, so this is a question anyone in the group can answer. Looking back, what would you say was the defining moment that made you confident Cradle could do this thing? So, is there anything you would to say?
Yes. Yeah, I can share a little bit first. So, some people they tell us like how strong your systems and how reliable your systems. And at some point, I find the defining moment is that after internal meetings, we have a meeting only for the 5 operator members in the operator meeting, and we discuss like what's just and what your mentally thinking. And after that, I kind of like very released and feel more confidence. And like agree we can actually make it. And also, the demonstrations is always the best way to show how strong you can do and how strong you can perform. So we have multiple demos before the actual deployment in Germany. We have like first internal rehearsal, and after that we go to the Formby Beach in Liverpool, and then we have a final 2.5-hour final rehearsal the day before we go to Germany. So we have 3 demonstrations before that. So to let you be more confident and you know the system well for a long time, you know something along the behavior that it is because after trial runs, multiple trial runs, you know more about the system. And that's this moments I feel we can actually make it.
Very good. I think I was confident the team can start, quietly confident that we'll be able to handle the challenge. But so to answer the reverse question of at what point did I lose faith in the team, was at that Formby Beach trial. This was about 3 days before the deployment. And we'd previously done a lab test, a 3-hour lab test where we tried to, we were very strict, we wouldn't look at the robot, because that was one of the requirements. You couldn't visually see the robot. And our in-house tests went extremely well. I think we managed to dig something like 10 kilos, filter about 2.5 kilos of brick, cement, sand. So we were confident. Then we put the robot in a van and transported it to Formby Beach. And things that worked in the lab just completely stopped working. So the beneficiation system, we turned it on and it wouldn't vibrate, and there was this smell of burning coming from the electronics. Which was very disconcerting and heartbreaking almost when things that have been working stop working. I think a key takeaway was I was very grateful that we kept running those multiple tests and realistic tests. But we did manage to sort that issue. It was a fried speed controller. Yeah, confidence was restored. It's good.
I have a moment to share. Like there was a time when the hopper actually worked. So it's not only about excavation, it's how you're going to store it in your rover and going to drop it in the beneficiator. And the minute we are able to know that we're going to store 8 kgs with that linear actuator, what we built, and brilliant idea from Chris, we were like, okay, we're going to do a pretty good job in the competition.
Okay, great. So we'll go on more detail about the testing before going to Germany, but let's focus a bit on the deployment aspect of it now. In terms of design considerations and changes, to Chris and anyone who can answer, what were the biggest design considerations that shaped the current system, which is the MoLES3? And were there any features that had to be sacrificed or simplified in terms of the requirements?
The first one off the top of my head, where we simplified would be, we did go for quite a simple filtration system, essentially just sieves stacked together with a vibrating motor on. And that was just to do with time requirements. But also, we had on the back of the rover a hopper for holding the regolith. And initially, we had quite an elaborate tube or pipe system that ran down, and I think we took it to the workshop at Menton, and the engineer said, why don't you just use a tube? It'll be a lot easier to manufacture, and we just kind of went, yeah, that's a really good idea. And so that's why there is a big tube holding all of our sand. And then we also, there's a mechanism on the back, we had to be able to obviously release the sand when we want to, but not release it when we don't want to. And that mechanism, initially we wanted that to be passive. So when we reverse the robot into the beneficiator, the door would open just by engaging with something. So maybe it'd be spring-loaded. Because if you don't have, the idea was let's take as many motors off the robot as possible so there's fewer things to break. But as we were developing that game, we realized that the robot's height would change as it goes over the uneven surface. So getting a cam to align was actually really tricky, and it's actually just easier to have an active game that servos control that back.
Yeah, great. Okay. Right, so just to add into that, so yeah, again, with the conversation around being simpler and better in some aspects, but also having that less errors because we do have encountered a lot of challenges in terms of things not working. Right? So now my question to you, Danish and Sky, you both spent long hours in the lab. What were some of the toughest technical challenges you faced during integration? And of course, how did you overcome these things, such as software side, hardware side, and any last minute tech results that would impact our performance?
I would say the most difficult part of this system was mounting the tube, because we were using only 4 joints on the arm. The reachability was really limited. And for the reasons Chris mentioned, we were not using any lifting mechanism for the tube, so it has to be at angle, at certain angle. So the margin of error was really small, and it took a lot of trial and error to get that angle right. And to be honest, we were adjusting the angle until the last moment, and we were not sure how we'll do in the field. This is one problem.
Yeah, the angle of the tube guys is very difficult to adjust. Like Dennis said, we picked that position the last minute before we shipped the robot to Germany. Actually, I plan to fine-tune that positions at the time before we have that conditions, because we have 4 hours preparation time, and so I can test the final positions again. And from my side, I think the most difficult challenge is how to make the arm reliable for long-term missions and operations. Because if you have experience developing the arm for whatever task, like manipulating or pick up the object and move the object or do whatever task, the arm will die for some reasons. Die means like system shut down or lose power, or maybe the controller manager of the arm is unresponsive. That means the arm is died. And the arm could die for some reasons. One is that the arm reached the limits of all the joints. Another reason is maybe the arm hits something and the currents to power supply the arm, like over the limits of the currents. It could burn the hardware as well. Another reason is how the payload the arm can carry. If the payload is over the limits, each top of the motor. Over top can also die. So the difficulties is how to bring it back remotely because we have two tickets to consume during the missions. If you have some level failure or have some hardware failure, you can consume the tickets, which will reduce and deduct your points of the completion. And we don't want that. And we make it successfully. We didn't consume any tickets in 2.5 hours. And last and continue 2.5 hours, keep operating the game for long time of operation. And that's the most difficult part from my side.
Great. So yeah, that you just want to add into that as well that you have several layers of failure modes, right? And then we're able to use that during the deployment, which we will discuss later. Okay, so for everyone to answer, if you had one more month before shipping to Germany, what would you have changed or improved? Is there anything?
If we had more time and regular stimulant, we could have re-optimized the scooper because we built the scooper based on sand, building sand. It was okay in the testing, it was fine. But when we tested it with the stimulant, it behaved quite differently. And we only received the stimulant one day before the shipment. So we didn't have much time to make any changes. This is the only discipline where we lack in the competition. Because I believe we lose a lot of material in the transfer position, which was not the case with the sand. In other department, we did great. In every other department, we did really great. And I think this is the only limitation of our system. But
Yeah, if we have one more month, I truly believe I can make the excavations whole process much faster because I can simply shorten the trajectories for the arm motions by less than 40 seconds per iterations. And from simple calculations, we can know how much per scoop and then how many scoops we can have, like in the total missions. And in the completions, we take in total 9.6 kilogram of regolith, and I believe I can take more if I have one more month to tuning the systems and adjust the trajectories.
I think we could have also improved the structure balance as well, so that it's able to climb steep and more inclination. I think that's one improvement could have been done if we had more time.
With an extra month, I think from the beneficiation side of things, we worked out where the SIP would resonate, so that was fine. And adding more power to that wouldn't, to something that going along wouldn't actually help because if you're vibrating the motor faster, you come away from resonance. So the way we could have increased our vibrations is increasing the mass, the eccentric mass on that motor that we use for vibration. So I'd like to explore, I mean, we explored a couple of different mass sizes, but I think we could go higher, a higher amplitude in our masses. I think I saw some other teams, they used in their SIPs, they would have rotating brushing mechanisms to keep the material moving over the top of the SIP. I think given an extra month, that was something that we'd like to investigate as well.
Can I take that?
We covered it up.
Yeah.
Everything else.
Right. So of course, let's not forget the people who helped us. Right. So we have James, Kellen, John Berger from Amentum who were there for our sanity checks and design reviews. We had Andrew Warner and Sam White for the trial run as well as helping us connect with someone from Natural England who let us deploy in the Ainsdale Beach, which I have some videos of it actually right now. So we were able to go there and test the robot with the dogs as well. So at night. So this is not something I thought it would be impossible because of the a lot of permissions and last minute asks. So, but we were able to do it. And it's with the help of our network as well. So you can see here Sky setting up his base station on the sand. We got sand everywhere, right? So I guess yeah, we did very success. That's where it is not, right? So we're good, we're covered. But still, it's a nice experience. And as Grace has said, like, not everything worked in that testing, but it gave us an ability to test it because the environment is actually on dark environment. So we need to be what to get experience from operating in very low light conditions. Right. So we had artificial sun as well. So really thinking, and of course we have Kate and Marty for leading us in terms of academic and industry. We've got Chani who's helped us stay in the lab for long hours and testing, and of course to CRADLE management for the funds, because we wouldn't go far if we don't have this. This is the work of many people, by the way. So who else? Luis with the robot to lend us the Scout Mini base. Now we took it now and it's not going to be returned. Right, so it's permanent for Lisa. So I mean this project. So all right, so let's go to the third stage, which is the development, the big moment. We're the first team to deploy out of 8, which has pros and cons, but of course, to Chris, what did being the first team on the field mean in practice? And did it help or make things more stressful? And to everyone else as well, how did so is that, what was that time? The first team?
I think we were quite, we would have preferred, I think, not to go first, but there were some advantages to it as well, because we arrived and I think the way it was run was every single team would, there was a bit of overlap. So the final team would be, while one team would be packing away, the next team would be deploying. So when we arrived, there was no packing away, so we could have had run at the control room, workshop, weren't tripping over anyone. Going first. Yes, I think because we went first, we were the first person to try the ESA network, and perhaps Guy, you could talk a bit about that, if you want to elaborate on that.
Yeah. Regarding the MoLES network, we have two options to choose. One is use the ESA lunar network, their own Wi-Fi network, and another option is you can bring your own network. But the disadvantage using your own network is the total weight of the router or the power consumptions are on your own. You need to put that into your budget as well. So it means that you draw extra power. So eventually our network consumes like 30 watt-hour, so 10% of the budget. So that's quite a lot. And this is the disadvantage of using your own network. But using the ESA network is uncertain because we don't know how good the network it is. And back to 1 month before go to Germany, we had the Alakandra seminar. It's another similar UGV deployment using MoLES3 remotely. And the presenters in that seminar say MoLES3 is not user-friendly using the network, and they didn't make it work. And that scared me a lot. I'm going to use MoLES3 using the Wi-Fi, the lunar network. But you don't have any chance to test it before. Because that condition is like just one go. Otherwise, you need to consume the tickets to execute the robots for whatever reasons. So this is one of the disadvantages. We test and use the network as first priority and as pendant, but the network didn't work for our systems. And somehow we we solved it. We helped them like troubleshooting using 4 hours preparation time to deal with the level. Yeah. And that is the one experience we have. And yeah, and I think we help other teams in solve that issue.
That's good. Yeah. So yes, a lot of pros and cons. Okay, now going into the Luna facility, which is quite a really nice facility, right? The question for everyone would be there, how did the environment compare to what you expected? Is it quite different, quite the same? What were unexpected things, items you encountered already, even for the people watching online streaming? Is there anything that you noticed, something that is different?
It looks a lot like, as you see online. I was surprised, I guess, how the dust, even walking around, it's sort of fine powder. It throws up quite a lot of dust, I think. When our system was digging and transferring regularly. Although it was a design consideration, it was still, we noticed, and you can see in the video, dust kind of smoking out the top of the hopper. I think one of the unexpected things was the data speed that we had on the network. We kind of hoped that we could just connect it and it work, but we had very high latency, something like 6 seconds in our camera feed. So we had to switch it to our own network, which worked well. And
Yeah, from the video you are watching, the environment is quite bright with the artificial sun. But there's another concern we need to think about is if you're facing another side opposite to the artificial sun, that will be very dark. So there is a very high contrast lighting there. We use some light vision camera that work very well, very good on the visions. So that is another experience we gained. So the light vision camera will have the visions for the lunar-like dark environment. And in terms of the sand and regolith, we find it that is really compact. And the compactness is more like wet sand. We knew it kind of like we knew it before, but we don't really have those amount of regolith to test the excavation. But at the actual deployment, I found I used the same parameter profile for the digging for another dig, but my arm cannot dig it very deep into the sand with the lunar facilities. But if I can have a full scope when I do this in the beach or in our hydraulic lab, but that record is really compact. It looks like powder, but well, it's really compact, cannot be clean.
Yeah, that's great. Yeah. Okay, so for those who are online, for Kay, Sharon, and Danish, of course, you had to watch online and from our live stream. What was running through your mind when we're doing? We only have 2.5 hours to accomplish this mission, and of course, there's only we're just viewing it from the screen. So what was running through your mind?
So in the start, every minute was critical, but when I saw the first batch delivered, I felt so relieved. So it was the time I thought, this is not a prototype anymore. This is a fully working system that we have been working so hard for the past 5-6 months.
I would say the panic actually started way before the competition because Chris texted me like, "Sharon, network is not working, we don't know what to do." And you also texted, Paul also texted me like, "There is a problem with this work," and I was sending codes to Chris like, all the fails it. This fails, upload this, it will work, and everything happened. It was a stressful morning. Then the competition started, and we had a problem, and we connected to our network, and it was pretty good, but every moment was panicking, like, what is going on? And there were moments like Sky was digging everything up, like whatever he can see, he was digging it up, and it was a pretty good moment. And I think we collected a pretty good amount of evidence as well there. So yeah, from people from here, it was a stressful moment for us.
I think, and I didn't realise this at the time when we had the 4-hour demo, but while I was simultaneously asking you, oh, can you help us with the code to get our controller to connect to this new network? You were simultaneously presenting the live stream. So so you were actually trying to deliver and present and write code at the same time, which I didn't realise that's what was going on. So incredibly impressive.
Incredibly great. Anyone?
Yeah, I guess from our perspective, we weren't hearing much about what was happening with the team. It was very much, we were like hoping everything was okay. We were just, worried if things were, especially when there was a delay at the start, and then we had to wait half an hour, I think it was, to start again. But I think once we saw the excavations coming through, and there was like 1, 2, and it kept going, we were like, okay, yes, we're doing this.
Great.
It's working. It's nice.
Right. Okay. For interest of time, so we move on to our final section, which is what were the biggest lessons learned, and to wrap up. So to close, let's go around the group. What's your biggest lesson learned from the MoLES3 journey, and something that you carry into future missions, or perhaps advice for teams that will take part in the next ESA Space Resources Challenge and the next CRADLE Ideas deployment?
I would say in such competitions, simplicity and a reliable system is more important than adding extra features. Because initially we a lot of features that were making our system more complex and were taking more time to develop. So I'll say focus on the working system first. And also I'd say if it is not broke, then don't fix it.
So my biggest lesson learned is we always need to think from a positive way, but plan for the like a pessimistic way. You need to plan for the worst case. And I suggest to have always have a fallback or contingency plan for every single component. For example, cameras, we have 5 cameras. So if one fail, you may have some another overlapping to supplements and can be a backup for a certain circumstances. And even for the onboard computer as well. I use Intel as an onboard computer for our rover. I use the exact same model with same config as my teleoperations PC. So in case my onboard computer dies or broken, I can easily switch my operation PC to act as an onboard PC. And in terms of joystick as well, I have 2 PS5 joysticks to control the arm, and I can use another one as replacement. And even for batteries, you need to think and have this concept for every component, even software side. If one like software mechanisms fail, you need to have another fallback solutions or fail rescue solutions. Let's say if the system fits, sometimes the Linux system will also fits, right? Without any reasons, it just fits and it lost the UI, the mouse, nothing is working. And you need to find a way, remotely to reboot the system. And that kind of concept, you need to have a contingency plan for every modules and for every task. That's important. That's important.
I would say a couple of key takeaways are for every task, there is a correct way to do the entire stuff and there is an efficient way to do it. And these things actually taught me that how to do it efficiently. It's not about creating a complex structure, it's about how efficient the structure is going to be. And the amount of connections I was able to create because of everyone, like the contractors, the past the other engineers and the technical team in the universities as a first year PhD is like a very big connection for me so that I can use for my other future projects as well. And the way the team or everyone came together, even if it's for a sub task, it doesn't mean like it's a one-man job. Even if you don't know, other people can actually help you with it and make you learn a lot of stuff. I think it was a really good, pretty much teamwork.
Yes, lessons learned. So test a lot and test early was definitely a lesson that we learned. So things that were working stopped working after around 10 hours of working. So definitely test a lot. Other learning takeaways. Yeah, there's plenty of technical learning takeaways that will probably be very random for me to talk about. But I think in times we took inspiration when we had something to do from everyday objects. So, for example, that gate on the back of the hopper was inspired by mason jars, so like keeping your pasta or your oats in, because they have a silicon gasket around the edge, and that is really useful for just locking in particles. And that, like, you wouldn't notice it just looking at a mason jar. I certainly didn't, but the gasket, it doesn't like completely flat, because if you close again flat gasket, you have to have very tight tolerances in where you put your hinge joint so that it doesn't stay slightly propped open. But it's actually it sits above a fillet, so the shape of the gasket is curved. It's really niche and random, but it's something that I thought was really beautiful. It's something you see in everyday life. Is that changed the whole tolerances of the where that pivot point can be. I mean, it's much more forgiving. I didn't really realise what it was for until I just copied the design, printed it, and then started testing it. And the one with the filleted gasket could hold something like 5 kilos of more than just having it in the flat. So basically, random mason jar, sorry. Any lessons learned about
Us.
The team, this teamwork effectively, and I think, that's a really important part of it, having the can-do attitude that everybody did that and made it really work successfully.
Good. Right. So for me, it's the participation of everyone involved. Even we had MSc robotics students who participated with us, MSc aerospace, I think, as well, and we have PhDs. And so this is really participation of everyone involved. So I know that there's a lot of people here who are from the MSc cohort as well as the PhDs. So this will be you in the future. So just network, I guess. That's how you do it, and reach out to your instructors as well. So that's it. So okay, we might not have time for any questions, unfortunately, but if you have any questions, you will be able to reach out. I hope this run until 3 p.m. if you want to talk to everyone. For those who are online, there's a lot of you there. Please feel free to engage and reach out. And another thing that would be an opportunity for us is an event that is happening in the near future. So this is a good opportunity because we will have the ESA MoLES3 team demoing and you are able to see it in person. So demoing the kit, the robot, if you want to see it. So please watch this video. There's no video, but basically, we have the event here, which is our Robotics Innovation Showcase, happening on the 27th of November. Registration is open to everyone. Please register. It's going to be in the Renault Innovation Hub in Sister Manchester. It's near Piccadilly Station. It's an event that is participated and organized by 6 robotics cohorts. Namely the Center for Robotics and AI, Cradle, Rayco, Acorn, and Ring CDT, and of course the UK RAS network. So please do register and engage and meet the team if you have any questions. So, but that's all the time that we have. Thank you so much for lending your time to the panel. And of course the people attending in person and online. Thank you so much. Do stay updated on the latest happenings at Cradle. Yeah, sign up for our mailing list, and if you want to follow our social media channels, we have Cradle_robotics_AI. So there's so much things that are going on, and we can wait for you to know what's happening in the future. Watch this space, no pun intended. So, but again, thanks for attending the webinar, and until next time, see you soon. Okay, so thank you so much.